Hi guys, welcome back to Data Every Day. Today we're looking at a data set of women's clothing. So it's reviews from an e-commerce platform where we have a different review for each purchase along with a rating of that review. So what we're going to try to do is predict if the rating is a 5-star rating or not. The reason I'm doing that is because you can see there's quite a class imbalance, so it just makes our job easier if we limit the task to 5-star versus not 5-star. So if it's under 5-star, we'll give it a 0, and if it's 5-star, we'll give it a 1. And so I'm only going to work with these two columns. So this is an NLP problem. We're going to be using word embeddings, which is a form of learning representations of the words using deep learning. So let's hop into the notebook. We're going to be using NumPy and pandas for working with the data, and then just 3 pre-processing imports. We have the train test split function from sklearn, the tokenizer from keras.preprocessing.text, and the pad sequences function from Keras as well, from the sequence module. Alright, so let's go ahead and import all of that, and we're using TensorFlow to build the model. So we can load in the data using pandas.read CSV and grab the file path up here, paste it in, and we can then take a look. So here's our data set. So we could predict a few different things. We could predict the class name, which is like what type of clothing it is. Any of these we could predict. I'm going to try to predict the rating. So you could consider this maybe sentiment analysis, because if it's a 5-star rating, you can guess that the review is very positive. So we're going to grab these 2 columns. I'm just going to drop all the rest of the data because we're not going to use it for this task. So data.info will let us know if we have any missing values in those 2 columns. These are the ones I'm interested in. These are the maximum number of entries, and we do have some missing values in the review text column. So we're going to have to deal with that. Let's start pre-processing. So if we're going to use word embeddings, we have to get the sentences into a sequence, into sequences of integers, which is how we can then pass that in to the embedding layer from Keras, which will do all the work for us. So if we're going to do that, we need to do a few things first. First, we'll create this function called preprocess inputs, and this is that's a function. And this is going to take in a data frame. It's going to make a copy of the data frame, and for now we'll just return the data frame. So this way, wait, I wrote an equal, sorry. Okay, this way we can just pass data into this function and get back, for now we can call it x. This will just be a copy of data for now. So I want to drop everything except these 2 columns. So what we'll do, this is our labels, so let's just call that y. Y will be df sub rating, and then x is just this column, df sub review text. Now before I make this split, and I guess I'll return x and y, I do want to drop those missing values. So, so if we want to drop rows with missing reviews, because we can't make any predictions if we have no input. So basically, to do this, we can get the missing review rows by looking at this column, so x sub review text, and then calling .isNA on the column, and we'll have a true wherever there's a missing value. So we can then use this true-false Boolean series here as an indexer for our x. And you can see this will return just the rows now, where we have NaN in the review text column. And once we have that, since we can just grab the indices with the .index, and then drop these indices from our data frame. So that's what I'm going to do. I'm going to grab this, put it here, and just change x to df. And then we can say df equals df.drop missing review rows from axis 0, which is the row axis. And whenever we drop rows, we should reset the index afterwards. I'll include drop equals true to prevent the old indices from becoming a new column. Alright, and then we will split. We'll actually say we'll use only the review and rating columns. And now let's see what this looks like. So now we get back x. Oh, we should get x and y. Otherwise, it'll give it to us like a tuple. And let's see if we have any missing values here. Is na.sum to get the total number of missing values. And that's 0. So we're good on missing values now. I guess what's next is we should format y properly. So I'm going to put extra space here. And y is going to be, like I said, it's going to be a binary column. So let's make y a binary target. For this, we can take y and apply a function to it with the pandas apply function. And this, we can map this function. Basically, it's a lambda function that takes an input x. In this case, it will be one of these. This is our x. And for any x that it finds, it's going to return 1 if x is 5, and otherwise it will return 0. And so this will accomplish what we're looking for by setting any 5-star reviews to 1 and anything else to 0. So now, if we look at y, you can see it's just zeros and ones. To verify .unique will give us just 0 and 1. Alright, and now we can do our train test split. So I'm doing the train test split first because we want, when we're learning the vocabulary to use, we only want to use the vocabulary from the train set. If we want a realistic approach, we should save the test set as early as possible and consider the idea that we don't have access to the test set when we're doing the pre-processing. Because in reality, if you're using the model in practice, you won't have access to the data that's coming in. So you have to make sure your models fit only to the data you were trained it on. So we will now create 4 new sets of the data: xtrain, xtest, ytrain, ytest. That will come from the train test split function that I imported earlier from sklearn. We'll just pass in x and y and specify a train size. So we'll send 70% of the data to the train set. The other 30% can go in the test set. I'll include shuffle equals true and give it a random state. Shuffle equals true is on by default, but I'm just including it so we can see. This function will shuffle the data first and then make the split. And because it's doing a random shuffle, I'm including a random state so we can reproduce the results. So now that we have our 4 sets of the data, let's actually return those down here. Get them back over here. And now if we take a look at xtrain, these are just the reviews but it's only 70% of the data, of the original data. And the other reviews are stored in xtest. So if I look at the shape of this right now, you can see it's just one long vector. And I need to get this into a 2-dimensional input where each row is a review and each column represents a different word in the sequence. So what I could do is split the words, split the sentence but on white space, so I have a list of words, and then send each word to a unique integer. And that's what we're going to do with the Keras tokenizer. It's a very useful object that allows us to look at a set of text, find the most frequent occurrences, and then rank the words based on how frequently they occur and assign them unique integers in that manner. So we're going to learn the vocabulary. So let's create a tokenizer object. This is a tokenizer from keras.preprocessing.text. And we're going to fit the tokenizer just to the train set. So we call fit on texts. And we pass in xtrain, which is just the reviews from the train set. So let's return now. Let's print out the size of the vocabulary. And this is important when we're building our model. If the vocabulary is too big, sometimes, it can slow down the model, and I find sometimes it can actually make the model perform worse. Maybe it's too confusing to the model, and it can be useful to just limit it to the most frequent words. But if we're using a relatively reasonable number of unique words, something in the 10,000 to 30,000 range, usually that's fine, and we can just keep it, in which case we want to save the size of the vocabulary to use. So I'm going to create this variable vocab length. That's going to be, okay, I should point this out. If I just comment this out right now, whoops. And then if I return the tokenizer object down here, let's just get it back here, I'll call it t. If I look at t is our tokenizer object that has been fit already. If we call t.wordIndex, this will give us a dictionary with the actual mappings that it found. So it takes the most frequent words and it sends them to 1, 2, 3, 4, 5 respectively. So as this goes down, the words become less frequent. And we don't have to worry too much about the the unclean words in here. Because we're using deep learning to find similarities between the words, a lot of the pre-processing that you'd have to do normally with natural language processing gets taken out. Now, I'm not saying that no pre-processing will work. There may be some methods that can improve your performance. I recommend you test it out to see what works. If you really care about optimizing the model as well as you can. But for the most part, it's not nearly as important as if you're using other natural language processing techniques. So we want to take the length of this. If we find the length of this dictionary, we can see how many words we have. And we have 12,725, which is a reasonable number, like I said. Now, I would like to point out, when we're saving the vocab length, I do want to add 1 to this value, because we want to account for the 0. Now, the 0 wasn't in our mapping, but when we pad the sequences, because we want to make them all of the same length, we're going to use zeros to pad. And so this plus 1 accounts for that 0 character. So in here, vocab length is going to be length of tokenizer.wordIndex plus 1. And we can print it out, might as well. Vocab length and vocab length. And I'd like to, okay, we could, yeah, why don't we return it at the end here? And we'll store it in like a final variable like this, vocab length. Okay, so now if we run this, we should, yeah, it prints it out. I'll put a colon. And next thing to do is actually transform the texts. So we're going to convert the review texts into sequences of integers. And to do this, we can use the tokenizer.texts to sequences. And this will use the fit to just map using the word index that we saw earlier. So we want to apply this to xtrain and store the result in xtrain. Now we also want to do this to xtest. We already fit it to xtrain, but we're going to transform both xtrain and xtest using the same fit, like so. And once we've done this mapping, we're going to find the maximum sequence length, because we're going to need that if we want to pad the sequences to all be the same size. So find the maximum sequence length. And to do this, well, we can take xtrain, which right now, if we return it, if we look at xtrain.shape, oh, it's actually a list, so we can't see the shape. It looks like this. So basically, it's a list of sequences. It's really lagging because there's like 12,000 of these. But you can see each sublist is a sentence, and each integer is a word in the sentence. So right now they're all of different lengths, and we'll close this out because it's lagging up my whole notebook. But we want to make them a uniform length, and let's also save it as a NumPy array. So the pad sequences function will actually do both of those for us. But first we need to know how long to pad the sequences. So if we take xtrain and we convert, we could apply a function, we could map a function to this list. So the function will apply to it. We'll just send every sequence to the length of the sequence. Right, so for every sequence in xtrain, we're taking that x and just changing it into its length. And what's nice about that is if we turn that into a list now and take the maximum, we can just get the maximum length of any list in the sequence. I mean, in the set of sequences. And we'll call that max sequence length. Might as well print this out as well. Maximum sequence length and max sequence length. Alright, and we'll return this too after here. and we'll get it back as another final variable. Okay. Oh, what happened? Not enough values to unpack. Oh, did I not run this? Okay, there we go. Alright, so I printed it out. It found the longest length was 115, and the vocab length is, like we saw, 12,726. So now let's pad the sequences, because these are still just lists of lists. Let's use, so let's say pad the sequences to be uniform length. And we can use the pad sequences function from Keras. This will take in what we want to pad, which is xtrain. We'll also do it to xtest. We specify a maximum length that we want to pad to, and we'll make that max sequence length. And we'll specify padding equals post. You can make by default padding is pre. I like post. I'm not sure if it really has much effect. Basically, are the zeros at the end of the sequences or at the front of the sequences? Alright, we'll store the result back in xtrain. Alright, so let's do the same thing for xtest. And I think we're done pre-processing. We get this back now. If we look at xtrain now, xtrain is now a proper NumPy array with the sequences all of the same length, and they've been padded with zeros so that they all are of length 115. So let's just look at the shape. We have 15,000 examples and 115 inputs, each one for a different word. Xtest, also 115. So whether or not there is a longer sequence in xtest, it doesn't matter, since we are only fitting to the train set. Alright, now let's construct our model. So training. I'm going to start with just creating an input with tf.keras.input, the shape of which, so this is xtrain.shape sub1, or the second dimension of xtrain, 115. We could also put max sequence length in here, but I think this makes more sense. Then our first layer is going to be an embedding layer. That's tf.keras.layers.embedding. And the embedding layer, like I said, is going to learn representations for the words. So for each unique integer, let's look at xtrain. For each one of these, it's going to find a spot to send it to. By spot, I mean we pick some dimension of a vector space, and we can then represent each integer as a vector in that vector space. And if we just we use the weights in the model to actually learn where to send the integers, the words. So it's called word embeddings because we're embedding these words into some high dimensional vector space of our choosing. So for this layer, we have to specify an input dimension, an output dimension, and an input length. So the input dimension, this is okay. So if we were to one-hot encode these numbers, each number, the encoding of each word, which is one of these, the encoding of each word would be of length 12,726, because there'd be all zeros for 12,725 of the entries, and 1 wherever that word lies. That's called a sparse encoding, and it's very memory inefficient, especially when you're dealing with such high cardinality like this. So this word embedding is a type of dense encoding, which is a way to pack more information into a smaller set of numbers, essentially. The input dimension is the dimension of the original sparse encoding of the word. So that would be this, our vocab length. And we've stored it in this nice all caps variable here, so that input dimension will be vocab length. And you can see now why we have to add 1 to it to account for the 0. Then our output dimension. This is our choice. Generally, the higher dimension you pick, the more information you can capture, the deeper the patterns you can capture in the between the words. Something like 128 sounds good for this task. I'm not going to go into optimizing though. You could try out different values. Then the input length. This the input length is basically just how long is each input. I'm not sure if this is actually a required argument, but we're going to specify it as max sequence length. Alright, and we'll pass in inputs to this layer. Once we've embedded the words, if we run this and we take a look at X, you can see the shape becomes, well, let's look at inputs. The shape starts as a single, this is for a single review coming in. A single review coming in will have 115 inputs. So it's a single vector of length 115. Then that 115 long sequence is mapped into a two-dimensional array of 115 by 128. And that's because each word, which originally was just a single integer, is now represented as a vector of length 128. So you have all these 128 long vectors, and 115 of them, one for each word. And then once we have this, well, one thing we could do now is flatten this out into a single vector and try to classify on it. And you might get some decent results from this. Let's actually, why don't we try it out? We can flatten, tf.keras.layers.flatten, pass in x. That will just straighten out the two dimensions into one dimension, and then we'll predict with a dense layer. We'll just return one value with a sigmoid activation, which will be the probability estimate for the positive class. We'll pass in x. We'll create our model with tf.keras.model. The inputs will be inputs, and the outputs will be outputs. Then we can compile the model with we'll use an atom optimizer, binary cross entropy loss, and metrics. We'll just use accuracy. Okay, last we'll fit the model, store it in history, training on X train, Y train, give it a validation split of 20%, batch size can be 32, we'll train for 100 epochs and employ a callback function, tf.keras.callbacks.earlystopping, which will stop the model when it stops improving by looking at whichever value we pass into monitor, which will be validation loss. When the validation loss stops going down, after 3 epochs of no improvement, we will stop the model and restore the best weights. Restore the weights from the best epoch. Let's run that. I misspelled that. There should be 2 T's. Okay. Now, actually, let me enable GPU acceleration. It's not so important for what we're doing now, but what we do next is very important for. I'll do it in a second, actually. Okay, so it looks like the loss might be going up now. So, yeah, it's going back up. This was our best epoch, so the early stopping should kick in here. Yeah, and restore the weights from this epoch. So let's evaluate this on our test set. So results, model.evaluate, x test, y test, and we get an accuracy of about 0.796. So this is actually surprisingly good. This is very similar to what I got using a recurrent neural network. So basically what this means is just by knowing the presence of words, the model can predict accurately with about 80% accuracy. So let's see if this makes any difference. I'm not sure that it will. Now, I didn't try it with just the embeddings before, but we can use a recurrent neural network, a recurrent layer, to capture the time dependency between the words. So right now, the model just sees each word independently, and it thinks of each word based on its position in the sentence. The first word, the second word, the third word. It has no way to know the relationships between them across a period of time. So we'll use tf.keras.layers.gru, which is a gated recurrent unit. It's a simplified version of a long short-term memory network, or long short-term memory layer. Basically, it takes in each word one at a time, but also takes in a summary of the past words along with it. So each time it sees a new word, it's also considering where this word has been. So this has a number of units as well. These are just like neurons. How about 256? And we will return sequences, which means instead of just returning the end result after it's seen the whole sentence, let's return the result from every time step. So return sequences equals true, we'll have this result in a two-dimensional output instead of a one-dimensional output. And this uses a tanh activation, usually better than ReLU in this case, in my experience. Okay, so let's run this. Oh yeah, for this, these will take a while, really long time. So I'm actually going to enable GPU acceleration. And I'll resume the video when this completes. Alright, so it completed. And it's very interesting. In this case, it seems like we actually got a performance decrease. This was our old accuracy from just using the embeddings. And we now have 0.78, so it's gone down by about 1% accuracy. And you can see the best epoch was the first epoch. So sometimes in this case, we can try this, which we can wrap the GRU in a bidirectional layer, which will allow the model to look at the sequence both forwards and backwards. So that's just tf.keras.layers.bidirectional. And sometimes this can improve the performance. We wrap the GRU in the bidirectional. And instead of passing x there, we pass x here. Alright, let's see how that goes. Yeah, so I'll resume this when that finishes. Alright, so it finished, and that actually reduced it even more. So I really can't, it's on a case-by-case basis. It's sometimes, I guess, looks like the recurrent neural network is actually not working so well. So maybe then we can try return sequences equals false without the bidirectional, because that did not seem to work. And so maybe just having a single input, in which case we don't need the flattened layer, because this is just returning one input. To make this easier to understand, why don't we split this? We'll print out model.summary, and I'll also plot the model using tf.keras.utils.plotModel. And I'll grab the rest of this, put it here. Now we can see what this is doing. So just pass it straight through right now. You can see first the words are embedded into sequences of length 128, and then the output of the GRU is just whatever we specify here. Before, if we have return sequences equals true, you'll see that we have 115 different outputs, each of length 256, because it's outputting the output from each time step. If we make this false, you'll see it's just one single vector, which is the last vector it comes up with. So let's see if that works. This usually trains much faster if we're dealing with a single vector. Yeah, I'm not sure what kind of effect this is. I have one more thing I'd like to try before we call it quits, and just go with the word embeddings. Wow, that really tanked it. Look, that almost did nothing. We're down to 55 on the first epoch, which we were doing much better before. Yeah, it doesn't seem to be improving. So that did not work. Last thing I'd like to do is try using the embeddings passed in along with the results from the RNN. So we can do that let's keep return sequences equals true, because we got terrible results without. Oh wow, it actually is going up though. Oh wow, look at that. It's going up after maybe it found some minimum that was hiding. Let's see how it goes on the test set. But this is the best result we have so far. That's just from word embeddings. Okay, so we'll come back to that in a sec. Yeah, but I would like to try passing in the embeddings and then also the output from the GRU. I'm really interested in this. Okay, let's just construct that. So to do that, we're going to take x, pass it into flatten, and then pass the output into outputs. And then I want to copy the word embeddings. So how to do this? We can do two flatten layers. word flatten, we'll call one, and GRU flatten, we'll call the other. They'll both be flattened layers. So word, yeah, let's rename these. This will be word embedding. This will be GRU. So inputs is going to be passed into word embedding. Word embedding is going to be passed into GRU. But it's also going to be passed into word flatten. So the word embedding is now being split between these two inputs. Then the GRU flatten is coming from GRU. Now we have two single one-dimensional vectors at the end, word flatten and GRU flatten. We'll concatenate them together using tf.keras.layers.concatenate. Pass in word flatten and GRU flatten. And then pass the output of concat into outputs. So if we run this now, we should see it branches. They get embedded. We pass the embeddings into the GRU, and then we also pass the embeddings straight to a flattened layer. So this final output that is making predictions on contains both the GRU outputs and the just flattened word embeddings. Alright, let's see how this went. Whoa. Oh no, I lost the model. Okay, because I recompiled it, I guess. Or no, I recreated the model. Alright, yeah, okay. Let's see how this goes. Alright, I'll resume this when this finishes. Alright, it finished. Let's see the evaluation. And we do beat it. No, it's not by much. There is some randomness here. Keras, TensorFlow is not so easy to make the results reproducible. So we can account for some amount of error between these two values. So we say they're roughly about equal. I guess the last thing we could try is just return sequences equals false, since that seemed to actually have some improvement as the epochs went on. And then only difference here is we don't flatten it anymore. We just pass GRU straight into the concatenation, since this is now outputting a one-dimensional output. You can see the word embeddings get flattened and then concatenated, and they also get passed into the GRU and then concatenated. Alright, see how that goes. Alright, it finished. Let's take a look. And just about the same. We're getting 79 for all of these approaches. So I'll just go ahead and leave it like this. It doesn't seem to matter so much. And that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.